everyone. Today my presentation is increased ethanol production of Clostridium thermophilus by metabolic engineering. This is the agenda. The first part is introduction. For ethanol, it can be biofuels used as a substitute or additive to gasoline to reduce carbon emissions. Also, industry use as solvent, disinfectants, and raw materials for production of chemicals such as acetic acid and acid. Besides, it can use medicine and food, using drug production and drinking alcohol. As for Clostridium thermophilus, is a thermophilic anaerobic bacterium known for its excellent cellulose degrading ability and high temperature stability, and is a potential strain in the production of industry biofuels and high-value chemicals. For gross environment, the optional gross temperature is high temperature, showing stable growth under anaerobic conditions. Cellulose degradation ability has a powerful cellulose complex that can efficiently decompose the plant cellulose and generate simple sugars. But we also have challenges. The low ethanol production and the ethanol production capability of natural strain is insufficient to meet industry needs, and the poor lactic acid tolerance. The growth is restricted in an environment with high lactic acid concentration, affecting the production efficiency of lactic acid and other byproducts, and improving cellulose utilization efficiency. So our objectives are: first, increase ethanol production, use metabolic engineering to delete competitive metabolic pathway, focus metabolic result on ethanol synthesis, and further increase ethanol production by overexpressing key enzymes, such as ADHE. In second, development of lactic acid supertolerant strains. Through adaptive experiments and gene editing technology, improve the growth ability of strains under high lactic acid concentrations, and develop strains suitable for industrial lactic acid production. Third, improve cellulose utilization efficiency by introducing cellulose and arabinose metabolic pathway co-fermentation of cellulose and hemicellulose is achieved. The overall utilization rate of lignocellulose is improved, and the generation of waste is reduced. The main article I referred is lactic acid hypertolerant Clostridium thermophilus. The LL41 was obtained from the wild-type strain LL345 through genetic modification and adaptation experiment. The LL41 strain achieved a high lactate tolerance by deleting the ADHE gene to improve lactate production and optimize its metabolic pathway. The strain has significantly improved the lactate tolerance and can grow in an environment with lactate concentrations as high as 35 grams per liter to 45, showing strong tolerance and has a higher growth rate and metabolic stability than the wild-type strain. The modified strain can grow stably under high lactic acid concentration, simplifying the fermentation process, and increase ethanol production by developing multi-product production strains. Clostridium thermophilus can also produce high value-added products such as isobutanol and lactic acid at the same time. For the rational and preliminary studies, mm, first, improve the ethanol production in the metabolic engineering of Clostridium thermophilus by deleting the PTA gene. The ethanol production increased from about 0.5 gram per liter in the wild-type strain to nearly 1 gram per liter, indicating that focusing the metabolic flux to the ethanol synthesis pathway effectively reduced the formation of byproducts in Clostridium thermophilus by optimizing the expression of the ADHE gene. The ethanol production efficiency was improved, with the maximum yield reaching 17 to 18% of the theoretical value. Secondly, introduction of the isobutanol and the lactic acid synthesis pathway by introducing the isobutanol synthesis relative gene, such as ILVC and D. Isobutanol production was successfully achieved, and an isobutanol yield of nearly 0.1 gram per liter was obtained in a small-scale fermentation experiment. In terms of the lactic acid production, LDH and PDH were introduced and their expression was optimized to reach 40 to 550 of the theoretical maximum value of the 0.78 more glucose. About our experimental approach, the step 1, identification and the selection of the target gene. Identify key genes related to ethanol production, lactate metabolism, and the byproduct generation. We can use genome and analysis and the metabolic network models to select target genes that need to be deleted or overexpressed, such as PDA, LDH, ADHE. Step 2, gene editing and metabolic pathway optimization. We can use CRISPR or Cas9 and the plasmid system to edit genes and optimize pathways. We also can use the gene deletion, remove the PDA and LDH genes to prevent acetic acid and lactic acid production. For gene overexpression, we can increase the expression level of the ADHE gene to increase the ethanol production. We also introduced new pathways, like the introduced gene related to the isobutanol synthesis to expand the product types. For step 3, adaptability experiment improves the tolerance of the engineered strains in high lactate concentration environment. We can use the Clostridium thermophilus was cultured in a medium with gradually increasing lactate concentrations, and the strains with higher tolerance were selected, and the mutation related to the lactate tolerance were analyzed by genome sequencing. For expected outcome, we first improve the ethanol production through genetic engineering optimization. It is expected that the ethanol production of Clostridium thermophilus will reach 70 to 80% of the value. This will be achieved by overexpressing ADHE to enhance the ethanol production pathway and removing PDA and LDH genes to reduce the production of byproducts. And second, high lactate tolerance. The modified strain can still grow stably under high lactate concentration environment. Key genes and enzymes related to the lactate tolerance, such as LDH and membrane-associated transporters, can regulate metabolism and internal environment stability under high lactate concentration. As for production, the introduction of isobutanol synthesis related genes in the lactate synthesis pathways enables multi-product to co-production of engineered strains. The last one, optimization of fermentation process. The modified strain grows stably under high temperature and high substrate concentration conditions. We also have possible challenges. Challenge one, inhibitory effect of high concentration of substrates and products. We can optimize cultural medium conditions to reduce the impact of inhibitory effects. Introduce acid-resistant related gene to improve the strain tolerance. For challenge 2, metabolic completion during the co-production of multiple products. We can adjust the expression level of the key enzymes, ensure the rational distribution of metabolic flux through metabolic flux analysis, and reduce the impact of competitive pathways. For challenge 3, technical problems encountered during the industry scale-up. We can, based on the small-scale experiment, gradually carry out pilot-scale optimization and use advanced fermentation control technology to solve problems such as gas distribution and temperature. About the timeline, we plan to spend 15 months to finish all the experimental process. That's all. Thank you.